Shrikant, we begin now. So let people join. So today we discuss the thin obstacle problem or synonym problem. I would just state it as boundary obstacle problem. Now, first let me start with a simpler version, which is a Dirichlet problem mixed with Neumann boundary conditions. Okay, so what I have is that suppose I have a domain omega, and this portion is say M in del omega, relatively open. Okay, and what I do is that I minimize square, okay, such that I specify the boundary values only on the complement of this M. Thus that U equals to some G on del omega minus M. So what I have is that inside U has to be harmonic. So the minimizer U has to be harmonic, the solution. It has to be equal to G on the boundary. And on this side, what I will have is that because of this, because it comes as the energy corresponding to the Laplacian, okay, and here I can sort of put up the test. I don't have any restriction over here, so I can put up the test function up and down. What I just have is that it will have zero Neumann derivative on M. Okay, it just comes from the formulation, okay, of the Euler Lagrange. So we know pretty much everything about this problem, right? And now we look at the boundary obstacle problem or the unilateral problem. Okay. Which is again the same thing. This is M, this is del omega, and what you do is that you minimize that of the square such that U equals to G on this part, okay, subject to the condition that on M U has to lie above an obstacle. Okay, so this is a portion of the boundary, a relatively open portion of the boundary that U has to lie above an obstacle. So we specify that, and U is bigger than equal to psi on M. So this is on del omega minus M, and this is on M.
What is the hypothesis on del omega?
You assume everything to be smooth. Okay.
Okay.
So eventually we will take everything to be flat. Okay. The key thing is to understand what can you say about a certain interface that I will mention. So the fixed boundary is kind of irrelevant in this. Of course, at the places where you put this unilateral condition, there you want this domain to have enough regularity, otherwise the whole theory will break. But I don't assume anything on the other portion of the boundary. So the M will be a nice portion of the boundary for all my analysis. Okay. So now what can I say about the minimizer? So minimizer exists by standard methods, okay, exists by Hilbert space theory. And what can I say about the minimizer? Again, I can say the same thing, that Laplacian U equals to 0 inside omega, U equals to G on del omega minus M. Minimizer, so let's call it U. I mean, I'm calling the same thing U, but I think now it's already too late to change it, or maybe not. So B, B, B. Okay, so minimize over all B, which has these constraints. Okay, so this is what you have. So let me write it more succinctly. If I need to speed up, I can do that at the very end. That is in the second lecture. Okay. So this is the minimizer, and now over here you can only put up the test function up, not the other way. So what you have is that this will be expressed by the fact that U mu will be bigger than equal to 0 on on M. And suppose this is the contact set. Okay. So suppose this is the set where U is equals to psi. Now outside this, and this is the region where U is bigger than psi. On this side set, you can perturb the test function up and down. So this would be the same condition as the one over there, which is the zero Neumann condition. So on the set, U bigger than psi, what you have is that del U by del mu equals to 0. Clear? And this is the outward Neumann derivative, okay? Normal. So this can be rewritten as minus Laplacian of U, which is equal to del U by del mu over Hn minus 1 measure of M. Okay? And I know that, and what is the other thing that I know? I know that del U by del mu of U minus psi is equal to 0, which comes from these two conditions, right? And the other thing is that del U by del mu is bigger than or equal to 0. So these put together are referred to as the complementarity condition, complementarity conditions, okay, or the Signorini conditions. Okay, so these are my Signorini conditions. Signorini conditions. Although the original problem, Signorini problem, is for the Lamé system in elasticity, but nevertheless there are several parallels with this problem. Okay, so now let us look at another version of this problem, okay, which is the thin obstacle problem, okay. And then I will say that in certain situation, or at least one situation, that problem would be equivalent to this unilateral boundary obstacle problem, okay. But let me sort of describe what is the general thin obstacle problem, because that is how I sort of had advertised my topic. But I will cheat over there, I won't be doing that, okay, the thin obstacle problem. The problem is that now I will have the obstacle sitting inside on a lower dimensional hypersurface. Okay, so what I will have is that I take a big domain and then I divide it into this. Okay, this is a lower dimensional subspace. Okay, and this space called is D plus and D minus. So D will be, and this is my M. Okay, so D will be D plus union M union B minus. Okay, and now what I do is that I place my, as the name suggests, thin obstacle problem on this thin space M. So M is like an n minus 1 dimension surface. So what I do is that I put a obstacle psi which lives on it. Okay, so I will be looking at this problem. So I minimize grad of B square over B plus union B minus, okay, because this is where the gradient lives, subject to the condition that, so let me write it down. So I will specify the boundary values G, okay, over here. So subject to the concept that B equals to some G on del D, and the constraint is B is bigger than or equal to psi on M. And now if I sort of, so what will the minimizer be? Again, the minimizer exists by Hilbert space methods, okay? So the existence is not the issue. So if U is the minimizer, what will U satisfy? U will be harmonic on D plus and D minus. So Laplacian U will be 0 on D plus union D minus. And now what you will have is that, again, this minus Laplacian of U that I had written over there, which is del U by del mu, but now that it will be more like there will be two normals, crisscross, right? Because the picture that I have drawn, it looks like D plus and D minus are symmetric, but in general, the whole surface can tilt a bit. So the normals, the outward normals can sort of be more crisscross kind of thing, right? So, and the whole graph can also tilt in the most general scenario. So this problem in some sense is harder in the generality compared to the unilateral problem. But I will be discussing later the symmetric case when both the problems match or they are equivalent. So nevertheless, in this generality, what you have is that you take this will be equal to, if you just want to mimic that, this will be del u mu plus del u mu minus, okay, depending on from which side you are coming. So minus is not there, times the hn1 minus measure of the set restricted to m. Okay. And the thing is that, and on the set where u is bigger than psi, you will have that del u mu plus del u mu minus is equal to 0. Clear? And otherwise they will be bigger than equal to 0. So what I can now do is that I can kind of try to write it like the classical obstacle problem. So I have a phi. So what is the notation psi? So there is a psi here. I put psi to be, say, minus infinity here and minus infinity over here. So formally, I can write this problem. So formally, and what I now assume is that, so suppose, so because you see that the graph can tilt in the most general case, so you can have at most regularity from one side. So suppose from either side, u is C1 alpha regular up to m. That is, suppose u is in C1 alpha of d plus minus union m. That is from one side, but across it could just, it is at most Lipschitz, okay, it can be across. But from one side it is smoother. And that is what you would typically have in these problems. Then I can do better, right? I can sort of write this, in the following way, that if I sort of combine this, and on the set where u equals to psi, you have that del u mu plus del u mu minus is bigger than 0, bigger than equal to 0. Right? So I can write this as min of the set where, so min of the set, and this is equal to minus Laplacian of u. So I can write this simply as minus Laplacian of u minus psi is equal to 0. Pretending that I have defined this to be the obstacle to be minus infinity on both sides, so they never meet. Okay, so this is like the formulation of the classical obstacle problem. Okay. And in fact, it turns out that these thin obstacle problems, or these even the Synorini problems, well, not at least the thin obstacle problems can be obtained as certain approximations of classical obstacle problems. And that is what Caffarelli, which I will mention in his C1 alpha paper, used it to show the quasi-convex. Okay. One thing, I'll mention that in a while. Okay, so you can happily ignore it for now. Now I want to look at the situation where, so in general, you see that these two problems are kind of similar, right? This boundary obstacle problem as well as this thin obstacle problem, except for the fact that over here there could be some asymmetry that makes this problem much harder to analyze. But now I will mention a very special case where both the problems match, and that is what I would look at for the rest of my two talks. Okay, for today. So now I take a very nice case, which is a ball, and ball in xn direction, and I take unit ball, and I take this boundary, which is the set where xn equals to 0, intersection b1, which is equal to b1 prime. This is my m. And then what I do is that I define g to be, I take g, which is symmetric. So x equals to x prime, xn, this is not enough. So g of x prime, xn equals to g of x prime, you can guess, right? You want this datum to be symmetric. Okay? And then, so you minimize, and what you do is that you take psi to be 0. Okay, you take this psi to be 0. Then you minimize that of u squared, because this is the case that I will look at, but for now, let us not take psi to be 0 because it will sort of create a misconception. It's not that this whole theory has been built for non-zero psi, and that creates a lot of technical complications as one wants to do the regularity assumptions on psi. And this has been a question of a lot of interest over the years. But so therefore, in the very formulation of it, let me not make that simplification too, because anyway, for psi it doesn't matter. because psi only lives on this set. Okay, psi only lives on the set where xn equals to 0. So you minimize this quantity subject to the condition that u is bigger than equal to psi on xn equals to 0. U equals to g on the boundary. Now again, in this case, because the boundary datum is symmetric across xn equals to 0, okay, and if you change u to u tilde where so therefore by the uniqueness of this, u has to map, u also has to be symmetric. Okay, if there is a minimizer and the boundary datum is symmetric, and x prime comma xn going to x prime comma minus xn doesn't change the energy. Okay, so therefore the minimizer also has to be symmetric. Okay, so it is simple, quite straightforward. So this implies that u is also symmetric in xn, that is u of x prime xn equals to u of x prime minus xn. And then if we restrict ourselves only to this part, so let us call this part b1 plus. So if we restrict our attention now to b1 plus closure, that is including this thin boundary, then we get that this is equivalent to the boundary obstacle problem. So most of what I will do is taken from the book of Petrosian, Shagolian, and Podolcheva, okay, with some little difference. All right. So now let us say where these problems pop up. Okay. So the first one will connect to the half Laplacian. Now recall, and for this the problem has to be stated. So this is applications, okay, or motivation.
So this seems to be equivalent to the second problem, not the first one, because in the first one there is no mention of what happens to you on M. This is the second problem. You have some restriction.
No. Okay. Sorry. So this is let me clarify. This is the title of the talk.
Okay.
This has no beginning of what I described here.
Okay.
This is just a problem with no obstacle. Okay, because there are no Euler.
So yeah. So by this you mean that problem.
Yes. Oh, I think I shouldn't have mentioned the title. Okay. Yeah, so please don't get confused. Okay?
Yeah.
Because you were the one who told me to mention the title of the talk, okay, which I did, but in that process I made it worse.
What I meant is a result. Anyway.
Okay, anyway. So recall, I mean, this shouldn't even be called the Caffarelli-Sylvester extension in the sense that, I mean, you see, like for the half Laplacian is kind of well known. I mean, if you have Rn minus 1, which is identified with x prime comma 0, okay, you solve this now because it's I want to relate it with the non-local Laplacian, okay, half Laplacian, so the problem has to be stated in the whole space. So if you look at this problem, okay, yeah, then with the boundary values u, okay, boundary the same u I'm using for both, then what you know is that del mu of u equals to minus half Laplacian of u in Rn minus 1 of u, and del mu of u in this case is like minus del xn of u, because the outward derivative goes this side. Clear? So therefore, if I sort of identify that, what is it that I obtain? So this is the same as telling that min of, so this boundary obstacle problem is the same as telling that because I wrote the formulation in terms of the classical obstacle problem, is just telling me that this is equal to minus half Laplacian of u comma u minus psi is equal to 0. And so therefore this boundary obstacle problem is the same as the classical obstacle problem for half Laplacian. That is, you look for the least half superharmonic function which is above psi with some decay assumption at infinity. Okay, but at a local level this problem is the same as this boundary obstacle problem. Okay, so this is one motivation, and of course, I mean, this problem has been looked at not necessarily from this perspective, but even otherwise back in the 60s and 70s, which 60s by Signorini and Then, of course, Luis Caffarelli came into the scene. So I will be describing all such results. So let me not repeat. So let me try to avoid as many repetitions as possible. And so this has been in the kind of has surfaced for long. However, once the Caffarelli-Silvestre extension came, so then people started looking at the boundary obstacle problem for these kind of operators, which is divergence of xn to the 1 plus xn to the a of grad of u equals to 0. With the boundary value u is bigger than equal to psi, u is bigger than equal to psi. So this is exactly, if a equals to 1 minus 2s, then this will similarly xn, if you put xn to the a in the limit as xn goes to 0, then you can change this half Laplacian to the S Laplacian. So this is the Caffarelli-Silvestre extension. So this influential paper was written in 2007, and that has kind of led to a lot of development around local and non-local operators over the years, right? And this was kind of the starting point. And then the entire theory of this boundary obstacle problem was quickly implemented for the boundary obstacle problems for these degenerate elliptic equations in Caffarelli, Salsa, and Silvestre around the same time. And I'm sure that people use this paper as a reference for various regularity results that are kind of buried in the paper. But of course, the principal objective of this paper is to understand the optimal regularity of the solution as well as the optimal regularity of the regularity of some portion of a regular part of the free boundary, quote unquote. Okay. So, and there has been a lot of papers that have been written ever since, but I will only focus on the case when f equals to half. So just to let you know that these boundary obstacle problems, if you change the Laplacian to these degenerate elliptic operators, then they are related to this half S Laplacian in this manner. Now, historically, it seems like, I mean, these kind of extension operators, which is the one for this, were already known prior to Caffarelli and Silvestre. So they have been studied since 1950s by Weinstein, Hubbard, Stein, McEnhoff, and so on. And there is a very detailed account of all such developments in a very nice paper of a survey paper on called fractional thought. So he's my advisor. I mean, I'm not trying to sort of advertise this paper, but this is indeed a very good scholarly collection of a lot of developments that have sort of happened around, I mean, over the last 50 years. So this puts everything in a better historical perspective, but it only depends to what extent we would want to go back in time. So anyhow, so it also shows up in optimal stopping problems. Math finance, and so on. I won't even try to explain what these are. But the one that I will try to mention is the one that will give us sort of an approximation to this problem. Because that would be a problem, okay? That is a problem on osmosis, and that will sort of provide us the technology to approximate this problem. So this is more traditional. It goes, it even predates some of these other motivations, okay? I will try to explain very superficially what that is. So what I have is, say, so semi-permeable membranes. And these are all taken from the book. And I'm no expert, so I hope questions would not be asked, or you will be generous enough to ask me questions on this. Okay. So I have a biological cell which has some mix of, and here is a semi-permeable membrane which allows selective passage of smaller molecules but blocks the larger molecule. So I have a smaller concentration of solvents, and I have a large solute. That on the other side, I have a larger concentration of solutes. Now, because of this chemical imbalance, there is a pressure that develops, which is called the osmotic pressure. So semi-permeable membrane osmosis that drives the smaller molecules, which is the solvent, out. Okay, so that the overall concentration of the solute kind of balances. And this passage cannot continue indefinitely, right? So then what happens is that around this boundary, there is a pressure that builds up. Okay. So under certain good assumptions, okay, let's call that pressure U. This is the pressure that builds up such that, and if we are in the stationary case, although this should be looked at as a time-dependent problem, okay. So in the stationary case of equilibrium, what you have is that, let's call this threshold. So if pressure is below the threshold, the flow continues. If the pressure is above the threshold, the flow stops. So let psi be the threshold. Okay. So inside still, you will still have that Laplacian U equals to 0 because you have chemical equilibrium. And if in the region where U is say less than psi, okay, or if U is bigger than equal to psi, the other one, okay, what you will have is that, or U cannot be bigger than equal to psi, but U is equal. So U is the threshold. So if U is less than psi, the flow continues, okay, and this should be related as del U by del mu should be a certain function. Let me write it down. So, and then I will rescale this problem, and in the limit I will obtain this boundary obstacle problem. So the flow continues as a linear function, which is say minus of U minus psi. Why? Because U is less than psi, right? U is less than psi, and the flow has to go out. So I cannot take. So I have to take an additional minus to adjust it. Clear? Clear? Because U is less than psi, this has to be positive, right? Because the flow has to go out, and therefore the thing is that U minus of U minus psi is positive, right? So this is kind of the right linear dependence. And then what I do is that I divide it by 1 by epsilon. And then in the region where U has cross psi, U has cross psi, and otherwise equal to 0. Del U by del mu equals to 0. Okay. So that is, if the pressure has crossed the threshold, the flow should stop. Okay. Clear? So let us try to draw this graph. So if I call this graph as, let me put it. If I call this graph, so let me write this condition again, that when U is less than psi, del U by del mu equals to minus 1 by epsilon U minus psi. If I call this minus beta epsilon of psi, or just the beta epsilon of U minus psi, so how does the graph look like? So I have a graph which looks like this, right, for every epsilon. So it is at 1 of the order epsilon because the slope is like 1 by epsilon, right? So this is epsilon, this is at minus 1. And then it is 0, right? And now when you let this epsilon parameter go to 0, so this is the graph of beta epsilon. So this is as a graph. So the graph of beta epsilon converges to the maximal monotone graph. Okay, let's call it beta naught of U. And so therefore, in the limit as epsilon goes to 0, what you have is that del U. So let's call this problem the U epsilon problems. Okay, and so therefore, in the limit as epsilon goes to 0, when U epsilon goes to U, which is the solution to this obstacle problem, you have that del U by del mu is in beta naught of this of U. And what is beta naught of U? Beta naught of U minus psi. Okay, and what is this beta naught graph? This is the maximal monotone graph. That is, it is this whole axis below. Okay, and the fact that you have this inclusion is exactly the complementarity condition that I have perhaps gotten rid of. Okay, I don't seem to have it on the board. Okay, so the complementarity conditions for the boundary obstacle problem were that del U by del mu should be bigger than or equal to 0, and on the set where U is bigger than psi, del U by del mu equals to 0. And so because the thing is that of course you see that this has some negative portion, but by the time you go to the limit, you will see that there is no portion to the left of it. There is no portion to the left of it that will live. Okay, the only portion that lives is to the right. And so therefore this will go to a measure. Okay, and that is what makes the regularity issue somewhat involved, and therefore, I mean, it is a very legitimate problem to study. That it doesn't follow from the classical elliptic theory, because in the limit there can be a measure on this interface. Okay, so that equals to 0 on the set value is bigger than equal to size, and that is all, right? So u again in the distributional sense minus Laplacian of u is still equal to del u by del mu times the hn minus 1 measure of the set M in general, which is flat now. So u is superharmonic, right? Because the del u by del mu has a sign. Clear? So now what can I say about the solutions to this problem? So there is a way to approximate this problem by this beta epsilon problem, and a detailed account of that you will find in the book of Petrosian, Chagolian, and Uraltseva, and also Dua and Leon. But the exposition that I'm using is this modern one, Petrosian, Chagolian, and Uraltseva. So you can approximate the problem u by this beta epsilon problem. So if I had time, I would even do this. So, but given the scheme of things, this is a relatively softer portion where you get existence. Okay. So let me try to see what is the regularity of u. Okay. So now qualitative properties of solution. Properties of solution. So around 1979, Luis Caffarelli showed that. So, well, before that, let me give you some examples in the model case, okay? Because that will sort of demonstrate the equation better. So, some examples. Otherwise, the regularity makes no sense, okay? So, assume that M is the set where xn equals to 0, intersection G1 or G1 prime, and now let us look at this set. So, this is the set where, say, xn minus 1, you can take x1 or any of the other n minus 1 direction. This is, say, less than equal to 0. Okay, and now what you one example is you can check, you can take it with the real part of x1 plus xn minus 1 plus I xn to the power 3 by 2, which is if this xn minus 1 less than equal to 0, this will sort of slice up in a 3 by 2 way. So let me draw the picture over here. So, okay. So as you, so this is the set xn minus 1 less than equal to 0. It will slice up, okay, and far away it will develop a wedge, okay. And the wedge becomes flattered by the time you reach this origin, okay, and this leaves at a 3 by 2 rate, okay. So, and there are other examples. Other examples are where you can take UK in general. I could have written real part of xn minus 1 plus I of xn to power kappa, where kappa is 3 by 2, 2, 7 by 2, 4, and so on. So kappa is either equal to 2n minus half or kappa equals to 2n. Okay, so these are some two-dimensional solutions that are known. So what do you need to do? You need to check that it satisfies the Euler-Lagrange conditions, and then it has to be the minimizer because the whole functional is convex. Okay, so these are explicit solutions, and in dimension 2, if there are any homogeneous solutions, okay, it's not difficult to see that these are the only solutions that can appear, because in dimension 2 you can use polar coordinates, sines and cosines, so you can see that these are precisely the solutions that are there. So this is the case when kappa equals to 3 by 2. So from this you see that, at least from this example, you see that if you look at this example, it gives you an impression that the solution cannot be better than Lipschitz, right? Across, right? Because you see that it's sort of, but however, as you get close to this xn minus 1 equals to 0, you see that it is leaving at a rate which is more than 1, 3 by 2. So therefore, that tells you that this is kind of a deceptive picture. But if you look at one side of it, that is when xn is bigger than equal to 0, from that side, you have a better regularity. So And this example suggests that the best regularity that you can get is C1 half, right? C1 comma 1 half, right? You cannot do better than that. So what are the developments on regularity for this problem? So now I think, I don't know why I gave such a motivation and talk with this. I did, but I have another lecture to catch up. Okay? Here I can sort of reduce my description of this entire thing because I will stop only with certain points on the free boundary. I will not do the rest of the points because those have been addressed later by different authors, which I will mention. Okay, so I don't have to do both the regular set as well as the singular set. So I will be done with the regular set, which I will define appropriately what they are. So regularity. So in 1979, Caffarelli using C1 alpha. And these are based on fairly geometric quasi-convexity estimates along the same lines that we had for the classical obstacle problem. Okay? And that is based on the extremal operator consideration. That is the least superharmonic function. So in fact, even for this boundary obstacle problem, it is also, you can also characterize it in the extremal sense. You can say that you look for all superharmonic functions which are bigger than equal to psi, okay, in the sense of traces, and then you take the infimum of that. That you can show it equals the solution to this boundary obstacle problem. So the obstacle is now on the boundary, which you can make sense in the trace sense. Okay. So Caffarelli showed that the solution is C1 alpha, of course not inside. So let me sort of write it in a better way. U is C1 alpha log B1 or C1 alpha B1 union B1 plus closure. That is up to the set xn equals to 0, U is C1 alpha. Away it is real analytic because it's harmonic. So the real difficulty is as you get close to 0. Okay. So here he showed that U is C1 alpha log, and this and it can be extended in that manner up to B1 prime. Okay. So it's C1 alpha up to the boundary, up to the thin set. And so as I said, these are based on quasi-convexity estimates, and it's a fairly geometric argument. And I don't think for these two lectures that I have kept, I would be able to show Caffarelli's proof, although it applies to a much wider variety of situations than the proof that I will describe, which is due to Tyndall error. So after Caffarelli, several people came up with proofs, and Tyndall error was one of them. Tyndall error. Maybe around 81, so this is 79, and that exploits some arguments. So that has arguments somewhat in the spirit of Luis Caffarelli, but it is both analytic as well as geometry. But I like this proof also because it also exploits the synonymy conditions in a very good way, or the complementarity conditions in a very good way. And there is another proof due to Kuracheva and also Arkhipova and Kuracheva around 1985, I suppose, which are based on DiGiorgi method, and that applies even to parabolic CT. Okay, so for the first part of the proof, so this is now any alpha, okay, but this one says that the optimal alpha should be half, if at all, or you should be able to find examples where it is below that, right? So anyhow, so first let me show this result of Luis Caffarelli, but by this method of Tyndall error. But finally, when we start understanding better properties of U and the free boundary, we will follow the approach of Caffarelli, Akanatopoulos, and Salsa. Okay, so this is only one topic where I am deviating from Caffarelli's proof. Okay, but this is just for the brevity of time. So I will show the C1 alpha regularity. Okay, now
Sorry. So for that first example, so isn't this supposed to be harmonic on when xn is positive, right?
Yes, of course. So it indeed is, right?
So x plus iy power 3.
Because it's like the real part of z to the power 3 half. And z to the power 3 half is, if you leave the branch, it is sort of, what do you call it? It is holomorphic. So the real and the imaginary parts are harmonic. Now I understand it's a very deceptive picture, but the harmonicity is not felt in this region. You have to stay away, which is impossible to draw in this picture. Or you have to be a great artist. So this is one thing. So what was I doing? Proof of C1 alpha, right? Okay, so the proof of C1 alpha is based on the following W22 kind of estimate. So I should name the problem something. So I have what is the problem? So the problem is Laplacian of u equals to 0 in V1 plus. U is bigger than equal to 0 on V1 prime. The thin space Uxn is less than equal to 0 because minus U or minus Uxn is bigger than equal to 0 because that is the orthonormal derivative, and minus U of xn equals to 0 on the set where U is bigger than 0, right? When it doesn't touch, this is what happens. So this is my problem, and I will show that it is C1 alpha in half the set up to the boundary. Okay. So there are boundary values, but it doesn't matter, okay? Because this is slope boundary. So I'm staying away from the fixed boundary. And I'm just proving in half the set regularity up to this thin boundary. So what are the W22 estimates? Okay. So the W22 estimates are the following. So you have that add of UXK square over. So if x naught is on the V1 prime, that is x naught n equals to 0. Okay, then it's coordinate to 0. Then you have the following estimate over any b rho of x minus x naught to the n minus 2. Okay, is less than equal to constant rho to the n over b2 rho minus b rho. So you can take it to the plus. Okay. Or what you can do is that you can evenly reflect and take the full thing. Okay. So so what you are doing is that, because as I said, for this problem, I can evenly reflect. So if I evenly reflect, after even reflection, the problem that I have is minus Laplacian equals to 2 times or both the minuses go, so 2 times u of xn. Okay, clear? And this lives on the set where u is bigger than 0 on the U prime. This is a compact representation of the synodic problem. Okay, and then ux squared, and this happens for k equals to 1 all the way up to n. Now this may be familiar to you. This is nothing but the energy inequality with the Green's function inside, right? And what is the proof? The proof of this is based on the fact that uxk plus and uxk minus for any k are subsolutions. For k equals to 1 to n. Now, let me just tell you, if I give you u to be bigger than equal to 0, subharmonic, in your regular Cacciopoli estimate, if you use in the test function the fundamental solution, you will get this estimate. That is, instead of taking the test function u times psi square, what you do is that you take u times g times psi square and you plug it in. Use the fact that minus of Laplacian g equals to the Dirac one, okay? That is that it has a sign, it is therefore bigger than equal to 0. You can throw away one term, you will get exactly this estimate where this u will replace the quantity, this uxk, okay? So this is a very easy exercise, okay? So in the regular Cacciopoli estimate, what you do is that you multiply the test function is u times psi square, where psi equals to 1 in b rho and it becomes 0 outside b2 rho. That is where you capture this gradient, but you multiply it additionally with this fundamental solution at the center point, okay? And use the fact that minus of Laplacian of g is bigger than equal to 0, u is non-negative, to get an estimate where uxk will be replaced by u. And now what we do, if we know that both uxk plus and uxk minus evenly reflected are subsolutions, so therefore this estimate is valid. That's all. But now how do I show that this uxk plus and uxk minus are subsolution? Well, it's not much, because so for this I have the general fact if I have, suppose, so this is based on the following lemma that says that if Laplacian of u is bigger than equal to 0 in the set where u is bigger than 0, then u plus is subharmonic in the distributional sense. Have you all seen this lemma? So what are you doing is that on the set where u is bigger than 0, it is a line, and then you are just extending it by 0. So you don't see the region where it could be 1 clone y. And this is a convex function. And how do you prove it? You prove it exactly the same way, except for the fact that you just cut things off to be used as a test function. Okay. So what you do is that you take qualification, this not qualification, sort of a cutting off of u based on the level, which is say phi epsilon of t equals to 1 when t is bigger than equal to 2 epsilon, it is equal to 0 when t is less than equal to epsilon. So it has a, so this is 0, this is epsilon, this is 2 epsilon, and this is how it goes, right? So sorry. The thing is that so this is 0 here, this becomes 1 here, and then it continues to be 1. So it's so when the derivative is supported, when the derivative of this is supported, this is convex, right? So therefore, I can choose psi prime in a way such that psi prime is bigger than equal to 0, and psi prime double prime is also bigger than equal to 0, at least in the region where the derivative is supported. Okay. So now what I do is that I use this in the formulation of this. So I want to know whether I want to know information of this phi epsilon of u. Okay. So what do? I take phi epsilon of u and multiply with a positive test function psi with a smooth set and non-negative. And then when you expand it, what you get is that this is equal to psi prime of psi times grad of u, grad of psi, right? And now what I do is that I write it as grad of u, grad of this entire thing, which is psi times phi epsilon prime, and minus grad of u, phi epsilon double prime times grad u times psi. And this has a sign. This becomes like grad u squared, psi double prime of psi, and because of convexity, and this is positive, so this is negative, right? Clear? Clear? And on this set, I know that u is harmonic, right? And so therefore, wait. What am I saying? So this is equal to this, and this quantity lives in the set where u is harmonic. So this is anyway equals to 0, and this is less than equal to 0. So therefore, this entire thing is less than equal to 0. That tells you that phi epsilon u is subharmonic. If phi epsilon u is subharmonic in the limit, you get u plus, which is subharmonic. Clear? Simple, right? This is solved. You just have to sort of track things in the right way. And now, how do I apply to UK ux plus and uxk minus? Now, let us look at any uxk plus. Any uxk. On the set where uxk is say positive for k equals to 1 to n minus 1. On the set where uxk is positive, the first ones, okay? I know that if it is in the bulk, it is harmonic because Laplacian u is 0. And on the boundary, if uxk is positive, it means that uxn is negative, is equal to 0. Then in this region, I can evenly reflect. It is the cross reflection. If you have zero Neumann derivative, you can evenly reflect. And then uxk changes to the same uxk across, right? Uxk also gets evenly reflected because k is between 1 to n minus 1. So it stays harmonic, right? Clear? So therefore, this is settled. And the same thing applies to uxk minus, at least for k equals to 1 to n minus 1. And now what can I say about uxn plus or minus? Okay. So what is significant is that uxn is like negative, right? Uxn is negative, evenly reflected. So uxn plus is subharmonic is fine. Right? Because I just check on the bulk region, I don't need to check at the boundary. The hard part is checking near this thin set. Okay, so let's look at only so uxn plus is fine. Uxn minus, if you look at it, so on this set where uxn minus is positive, uxn is harmonic. Okay, so everything is fine. It's an open set, right? So this is fine. This is so on the set where uxn is negative, uxn is harmonic, so this is fine. But on this boundary, if uxn is negative, that means that U is 0. So I can use the odd reflection. It becomes harmonic. If I use the odd reflection, then UXN gets reflected evenly because another minus comes out, and so therefore this UXN gets reflected evenly. Okay. So therefore, this also shows that this UXN minus is also substituted. Clear? And now I just apply it to this. Clear? Because if because in the tangential direction nothing changed, but if it is like if U of x prime xn is equal to minus of ux prime minus xn, then if you compute the uxn derivative, so uxn here, so u tilde xn equals to minus of uxn, and then there is a minus 1, so that becomes plus xn. Okay, there is another minus xn here. So when u is reflected oddly, the this normal derivative again gets reflected evenly. So this is fine. This is not the way I have proved it in my lectures where I use penalization. Okay, so this is quite formal. Okay, the way to do it generally, if you are approaching the problem by penalization, okay, is you prove it at the level of the epsilon problem that I have happily raised. Okay, that beta epsilon problem. Okay, but this is roughly the idea. So this is again the soft part of the theory, but you can prove it more formally. That is what I'm trying to say. Where is the problem? Because in the very first place, I would not even know that uxk plus is a legitimate Sobolev function. But for the penalized problem, I know a lot more. And therefore, when I pass to the limit, this is what I get. And at this point, these are very easy details to check that. You look at the penalized problem, pass to the limit, and this is not where the God is in the details. Okay, so there are certain places where the God is in the details, but this is definitely not one among them. So now, how do I use this W22 estimates, okay, to know that U is C1 alpha to this? And this is based on filling hole technique. I think this first came due to Whitman, okay, and filling hole technique. So what I do is that it's quite geometric, as you will see. So let me denote these quantities. I will define ik of rho to be grad of uxk squared over, and I assume that x naught is equal to 0. Okay, I do everything at x naught equal to 0. Okay, mod x to the n minus 2 b of rho, and this is for k equals to 1 to n. And now what I do is that I look at, on one side, I look at the region. I look at, this is rho, this is 0, this is 2 rho. I look at this region. On this region on the boundary, so let's look at this bigger problem. And what you have is that on this thin set, you look at this region, which is, this is rho, this is 2 rho. In fact, now I feel quite bad about my lecture. I didn't even define what is the coincidence set and this, that, but that I will do in my next lecture. Right now, I'm proving the regularity up to the thin set, and that doesn't see the coincidence set. It just sort of analyzes a certain sort of sign condition on this measure, which is del u by del u, or for the Laplacian. Okay. So it is not really central to the proof, but eventually, in my next lecture, when I try to understand the free boundary, which I will define, then you will it will look like I'm looking at a full-fledged free boundary problem. Okay, so this is low. So this is on the thin set. On this thin set, because of these W22 estimates that I have, I know that the trace is defined, right? Because in particular, this gives you that U is in W22. So therefore, in B2 rho prime minus B rho, there are only two possibilities. Either U is 0 or Uxn equals to 0. At any point, okay. Or in half the set. In at least half the set. That is on a good chunk of the set, either U is 0 or Uxn is 0. Both cannot be 0 at the same time, and this is to be understood in terms of the traces, thanks to my W22 estimates over here. Okay. So suppose the first condition is that Uxn is 0, okay, in half the set. So suppose Uxn is equal to 0 in half the set. Okay? In half of the ln minus 1 measure of B2 rho minus B2 0. And since I know that the trace is a compact operator in L2, okay? So therefore, I can apply the Poincare inequality. So by Poincare, first I do over B2 rho plus, and because of an even deflection, the same inequality is true in B2 rho minus, right? And therefore, I can take the entire B2 rho. So by Poincare inequality, this would mean that what you have is the following, that Uxn square over B2 rho, because these are all evenly deflected, right? So it should ideally be, so the boundary is over here. So the boundary is over this set, okay? So I'm looking at this set. And there is also this dimension that, okay? Because I mean, this sort of comes around, right? It's not like they're disconnected necessarily. It's sort of, they're like the annulus. So on this set, I'm applying the Poincare inequality, means I'm looking at the Poincare inequality in this annulus. I know that on the boundary, on a good chunk of the set, Uxn is 0. So the Poincare inequality is applicable, so I can control Uxn square by grad of Uxn square. Okay? So B2 rho minus B rho, I can control it by B2 rho minus B rho. Agreed? This I can do. Clear? Now what I do is that, and is it clear to everybody? I can do this, right? So now what you do is the following. You divide this side by rho, take 1 by rho square, but then in the W22 estimate that you have rho to the n, right? So you add plus n minus 2. And so therefore, this changes to this rho n minus 2. And now in the annular region, they are all comparable, right? To mod x to the n minus 2. So I can put this thing inside, and this becomes, so the new inequality becomes 1 by rho to the n of Uxn square over B2 rho minus B rho less than equal to a constant times grad of Uxn square over mod x to the n minus 2 over B2 rho minus B rho. And now what do I have defined that? This will be like in of 2 rho minus in of rho. So this is less than equal to constant times in of 2 rho minus in of rho by my definition. And this side dominates ik of rho up to a constant. So if I move this constant here, another constant here, that becomes c square, which I call as my new c. So what I have is that in of rho is less than equal to c times in of minus in of rho. Agree? And this just tells me that there is a decay. That in of rho is less than equal to c over c plus 1 in of 2 rho. And this is my theta, which is strictly less than 1. So this is in the case that Uxn is 0 in half the set in the boundary, right? On this thin set. In the other case, not displaced, this estimate I want to keep as it is, I guess. I end up conveniently erasing the wrong part of the code. Kind of. And by the way, like if I have time in the end, if you're not convinced with whatever I have written, I'm hand waving too much, I will even give you a proof of this, okay? But I just want to get to the central point, because this is just for you to check. You are all familiar with variational methods, you take test functions, you know how to integrate by parts, and there is no geometry in it, okay? You just have to apply it. Or at least I will not get the geometry that I can see, okay? So
Sir, there should be greater than equal to, because this...
No, I think it is correct. Just think enough, you will be able to trace it, okay? Because now I'm kind of running, I'm quite confident that this is correct, okay? So now on the other part, so the second alternative is that what? Second alternative is that u is 0 on rho prime minus p2 rho prime half, right? In half the measure. That means that all the uxk's are equal to 0 on the same set, right? Because they have a trace. So therefore, the thing is that I can apply the Poincare inequality to uxk. If I apply the Poincare inequality to uxk and apply the same method, what I get is that this would then imply that ik of rho is less than or equal to theta ik of 2 rho for all k equals to 1 to n. And now I do the following argument. This is not enough, right? Because then the thing is that I don't know which alternative I have. Huh? Oh, sorry. Okay. This is important. So now the thing is the following. When I go from 1 to 1 by 2 to 1 by 4, so on, or 1 by 2 squared to so on, all the way up to 1 by 2 to the k. Suppose 1 by 2 to the k is comparable to r, okay? A dyadic scale. Because if I know how to estimate on dyadic scale, the rest is real analysis, which I happily ignored. Then I know that at least half the time, one or the other alternative is satisfied. Either half the time one is, I deteriorate once, or half the time the other alternative happens. So that would first that this would tell me that either I should not call it K. Let me call it J. Right? Because I've used IK for there. Either what you have is that IK of 1 by 2 to the J, which is like IK of R, is less than or equal to half the time means what? J by 2 number of times, right? How does it matter? J is an even or not? Either it's the greatest integer of J by 2 or whatever. It's comparable to J by 2, right? Because you only care about small enough r's, right? Where J is very large. So it's whether it's J minus 1 by 2 or J by 2 or J plus 1 by 2. Nobody cares, right? Unless you are too precise about this constant. So then what you get is that this is less than or equal to theta J by 2 of Ik of 1, which is bounded, okay? And this is either true for k equals to 1 to n minus 1. And this would then mean that Ik of r is less than or equal to constant r to the alpha, that alpha gets decided by this theta. So alpha is like half of log 2 theta. Here I have to take an additional half because I could only do theta j by 2. Because half the time this happens means half the number of times here. Half the time here means half the set. So these two should not be confused. Okay, I'm using the same language for both, but they are different. Or if either this is there, right? If this happens, then I know how to estimate I and rho. Because I know that by the equation, because in the bulk region, ux and n is less than or equal to constant times xi summation over I from 1 to n minus 1. And therefore, this will tell me that In of rho, In of r is then automatically controlled by CR to the alpha. Because each of these IKs are. Using the equation, I can control the last one. Because in the grad of uxi, all the mixed derivatives are there, with the exception of ux and xn. But ux and xn is controlled by this, so therefore the whole thing is controlled by this. Clear? This is the first case. The second case is that at least j by 2 number of times uxn is equal to 0. And that would again give me directly, without having to go through this work, that In of r is less than or equal to constant r to the alpha. This is even easier. Right? I want to get a hold on In of r. Why? Because this gives me that the Neumann derivative is roughly folded. Why? Because after this I'm kind of done, and with that I will stop for now. So what do I have? So therefore, in all of these methods, what I get is that In of rho is less than or equal to rho to the alpha, say for all rho between 0 to 1 by 4. And what is In of rho? That is grad of uxn squared over x to the n minus 2 over, and this happens across all boundary points, right? Across B, rho is less than or equal to constant rho to the alpha. And now I can linearize this further. This is less than or equal to grad of uxn squared over 1 by rho to the n minus 2. And so therefore, this is also less than or equal to constant rho to the alpha. Right? Yeah. So therefore, if I apply the Poincare inequality, uxn minus uxn rho over any boundary point, centered at any boundary point, is equal to u minus uxn minus uxn rho square over 1 by rho to the n will be, so if you leave this thing aside, this is less than equal to constant rho square of grad of uxn square. Then this rho to the n comes. This gives you rho to the n minus 2, and this is less than equal to c rho to the alpha. So uxn separates from the average in c rho to the alpha way. That is what you need to do. So this is even stronger than the Neumann condition, right? And this happens across all. So this is when you take rho, but if you take any x prime, it still happens, right? So this will be replaced by b of rho x prime, where x prime is a boundary point. At this point, the Neumann regularity theory for the Laplacian tells you that you C1 alpha up to the boundary, to the flat boundary. And so later in the talk, I will update this too. So let me keep at least some part of the excitement. Of course, I mean, with internet you can find all the information, but we will continue in the later in the day, and we'll finish the rest of the theory.